Hello everyone, my name is Todd. I'm going to be your logic tutor today. Today I'm going to be introducing you to the rules of replacement that we use in natural deduction. A couple of things to understand. Recall that we have our special notation regarding negations. We have, in essence, a notation that means the opposite of, which we will use in De Morgan's and well, basically De Morgan's. One other thing, this little notation up here means is logically equivalent to. So, for example, in De Morgan's, which I have yet to explain, the expression on the left is equal to the expression on the right side and vice versa. Okay, let's begin by trying to understand what these rules of replacement mean. Okay, first, De Morgan's. What is De Morgan's saying? It's saying that if you have an expression that fits into this form on the left, a negated conjunction, and let's just come up with an example, B and Q, not B and Q, you may convert that into an alternative expression that means the same thing. So we're looking up here about how to translate it. So we push the negation through, as it were, and so the B becomes not B, the and becomes an or, and the Q would become a not Q. So wherever you have this expression on the left-hand side, you may convert it into the expression on the right-hand side, and vice versa. You can start out from here and convert it back to this using De Morgan's. Okay. So we can apply De Morgan's to a negated conjunction. We can also apply De Morgan's to a negated disjunction. And let me make this one a little bit more complicated, not B or Z. So we have not bracket, not B or Z, and we're going to apply De Morgan's to it. So we're going to push the negation through the bracket, as it were. So the not B would become a B. The or would become an and the Z would become a not Z. So this would be another case of De Morgan's, where we we applied De Morgan's to a negated disjunction. So we could go that way. But then again, if we had an expression like that, we can convert it to an expression like that. All right, let's continue on with another rule. Commutivity. Okay, so let's make this really simple, P and Q. And you might recall when we were doing rules of inference, we had the rule of inference simplification, and so if we had P and Q, we were allowed to say P by simplification, but we were not, technically speaking, allowed to say Q, even though it's valid. Simplification only allowed us to simplify the left-hand conjunct. Well, here is our workaround that I mentioned previously. If we have P and Q, we may replace that by Q and P, and our justification is commutivity. Okay, and then we could simplify to the Q if we wanted to. So any conjunction, you may rotate the conjuncts, change their places, and the same is true for a disjunction. So if we had not P or Z, we could replace that with Z or not P. Okay, so commutivity allows us to switch places on conjunctions and switch places of the disjuncts on disjunctions. It does not let us switch places for conditionals or biconditionals, so don't try commutivity on those, not allowed, only conjunctions and disjunctions. Okay, let's move on to another. Okay. Associativity. Suppose that we have a statement like B and C and D. Notice that the C is grouped with the D, but we could change that by associativity. We could change the grouping such that it's B and C and D. So all we did was move the brackets, and this is allowed by associativity. So if we have an instance of this, we can move to that. If we have an instance of that, we can move to this. Okay, so notice all of the operators in this were conjunction. We can do a similar sort of thing if all of the logical operators are disjunctions. Oh, let me change it to statement constants instead of variables. So let's suppose that we have Q or W or Y. The W is grouped with the Y. We can, by associativity, regroup things, so we'd have Q or W or Y. Okay, why might you want to use this rule? Well, you suppose that you want to get one of the disjuncts out of the disjunction, and you're setting up to do a disjunctive syllogism. You might need to move a particular statement constant to a particular place. Okay, let's move on to another. Distribution. Okay, now this one is a bit more complicated to understand, but let's suppose we have A and B or C. We might be able to distribute this A to the B and to the C. So here's how we do it. We're going to split this A up with the B and with the C. And now notice that the AND is the main logical operator. That main operator becomes the minor operator when we distribute, and the minor operator, which is the OR, becomes the major operator. So if you have an instance of what's on the left, we may convert it to the instance on what's on the right by the rule distribution. Okay? Similarly, we can do it where the OR is the major operator and the AND is the minor. But let's see that this makes sense first. Consider this on the left-hand side, and suppose it represents something like Bob has a burger, that's A, and fries or onion rings, that's B or C. Well, that's the very same thing as saying Bob has a burger and fries, or Bob has a burger and onion rings. So it makes sense that those two things are the same thing. Okay, let's do the instance when the OR is the major operator. We can distribute this to these items in here. Let's look at the pattern. We're going to distribute this, whatever this happens to be, to the circle and to the triangle. The major operator becomes the minor operator. So we have ORs here, and the